Everyone, this is Yunwen Cai. Today I'm going to present a class project of applied deep learning on detecting cancer metastasis on gigapixel pathology images. I'm going to first briefly introduce the problem and then introduce the methods I used and the results I got. So, a central component of breast cancer detection involves microscopic examination of lymph nodes adjacent to the breast, which requires highly scaled pathologists and is really time consuming. So the goal of the project is to develop deep convolutional neural networks to assist breast cancer detection. The methods I use for pre-processing is I use the 18 slides for training and validation at a zoom level 3. The way I select the patches is to first select a slide uniformly at random for 40 times. For each selected slide, I randomly sampled 50 patches of 128 times 128. So I got 2,000 patches in total. To reduce computation, I ignored non-tissue areas of the slides by removing background patches, which are patches with non-tissue percentage greater than 20%. So that is to say, if a patch has a non-tissue percentage greater than 20%, then I remove it and resample. So the 2,000 patches I got is after removing the non-tissue patches. I labeled a patch as tumor if at least one pixel in the region is annotated as tumor. The dataset is very imbalanced. The ratio of tumor versus healthy patches is roughly 1 to 5. So I rebalanced the dataset by upsampling from tumor patches. I also used the original dataset without rebalancing, and I used the dataset with downsampling as well. But they don't behave as good as upsampling, so I continued with upsampling the dataset. After that, I split the rebalanced dataset into training and validation set. And I also applied data augmentation to the training set, including rotation, shear, zoom, and vertical, and the horizontal flip. For modeling, I applied transfer learning using VGG19 with pre-trained ImageNet weights as the convolutional base. I fine-tuned the top convolutional block and the fully connected classifier, and I added early stopping by monitoring validation accuracy. For inference and evaluation, I selected 2 slides for inference at a zoom level 3. One of the slides I selected has relatively large tumor region, and the other one has a relatively small tumor region. By selecting these 2 slides, I hope they can represent the entire slides database we have. I slided a 128 times 128 window across the slide and record a sigmoid score for each patch. I generated a heat map based on the sigmoid scores. And for evaluation metrics, since the dataset is really imbalanced, I don't think accuracy itself can be representative of how good the model is. So I chose to use a couple of different metrics, including confusion matrix, sensitivity, specificity, precision, accuracy, and F1 score. So the result heat map looks like this. This is a test slide 1, which has a relatively large tumor region. On the left-hand side, I have the prediction, and on the right-hand side, I have the ground truth. So we can see that our prediction basically captures the red tumor regions. But also there are some small regions where we predict it as a tumor region while it's actually a healthy region. And the next slide has a relatively small tumor region. For our prediction is pretty bad, as we can see, because there's only a little red spot on the ground truth, which is the tumor region, but we are predicting it as it's tumor everywhere. So I'm thinking it's probably because since the tumor region is really small, the data set is very, very imbalanced. Our model is not behaving as good as the one with a relatively large tumor region. Oops. And for let's look at some numbers for modeling. On the right hand side, the table shows a couple of matrix we chose, and on the left bottom corner we have the training and validation accuracy. So we can see that our model is not overfitting since the training and validation accuracy is pretty close. That's probably because the dataset we use for training and validation is rebalanced. And on the right hand side, we have a couple of tables. These are confusion matrix of test and training and validation. So if we look at the blue region for training and validation, we can see the numbers are pretty close for training and validation, and they are pretty good. But for test result 1 and test result 2, the precision sensitivity F1 score is pretty low, and the accuracy and specificity is pretty high due to a very imbalanced dataset. And for test result 2, we have not a number because the precision and sensitivity is both 0, so we're dividing by 0. That's why we got not a number. I think imbalanced dataset is a really big problem because it's for test 1 we can see we have over 3,000 non-tumor region and only less than 100 tumor region. For test result 2, we have more than 20,000 non-tumor region and only 5 tumor region. So that leads to a problem. For the next steps, I think it's important to find a better way for resampling the dataset, probably, so we can deal with the imbalanced dataset problem. And also, we could try a larger image size, maybe 299 times 299. I didn't use that for this project because I don't have that much of CPU. And also, using multiple images per case at different zoom level is probably helpful since we need detail as well as context. That's it for my presentation for the Applied Deep Learning class. Thank you for watching.